Chapter 16 is all about acid-base equilibria. The following diagrams represent an aqueous solution of three acids, HX, HY, and HZ. The water molecules have been omitted for clarity, and the hydrated proton is represented as an H plus rather than hydronium ion. All right, A, which of the following acids is a strong acid? Well, as we know, strong acids completely ionize, so the one where there's no more HY left is HY. HY is completely split apart to form H plus ions and the conjugate base. B, which acid would have the smallest acid dissociation constant, Ka? All right, so a small Ka value means a weak acid, which means very little ionization. All right, so that's looking like HX. All right, very little H plus ion floating around. Which solution has the highest pH? All right, so high pH means low H plus concentration, so again, it's HX. pH is it's just a way of turning an exponent into a number that we can look at, right? So when I take the negative log of 10 to the negative 6, that's 6. All right, so it's a H plus concentration higher than 10 to the negative 7. If I have a H plus concentration lower than 10 to the negative 7, taking the negative log of it would have a pH higher than 7. So high H plus concentration, low pH. Which of these three lines represents the effect of concentration on percent ionization of a weak acid? All right. Percent ionization is a measure of how much a weak acid ionizes. So that would be C. You know, how much of this weak acid is disappearing compared to its conjugate base when I hit equilibrium. All right, so for example, if I had a 2 molar sample of hydrofluoric acid, a weak acid, right, it breaks apart to form X amount of conjugate base, fluoride ion, and X amount of H plus ion. So if I can solve for X, that'll be equal to the fluoride concentration. So plug these equilibrium concentrations into the Ka expression, recognizing that X is going to be inconsequential to your original concentration. So solve for X. And then we can get percent ionization, right? We take the X, which is the conjugate base concentration, and we divide it by the concentration of the original acid to figure out what its percent ionization was. So again, percent ionization is based on how much the weak acid breaks apart. So curve A shows the effective concentration on percent ionization. I'm sorry, curve C shows the effect of concentration on percent ionization. And for a weak acid, the percent ionization is inversely related to the acid concentration. Which of these three molecules shown here contains an OH group? Oh no, each of these three molecules shown here contains an OH group. But one molecule acts as a base, one as an acid, and the third is neither an acid or a base. So A, which of the following acts as a base? All right, so the blue molecule, the blue ball, is a nitrogen. So anytime you have an NH2 group, you've got an electron pair donated to an accepted H. So molecule A would be a basic solution. Looking at molecule B, that's the definition of a carboxylic acid group, right? You've got a double bonded O on that carbon, and that pulls electrons away from the hydrogen oxygen bond on that OH group, weakening it so that H will come off. So this makes this a acid. And if I'm looking at molecule C, you've got nothing pulling the electrons away from that OH group, so this can be a very hard H to take off. This would be this would be a non-acid. Wouldn't be an H acceptor, wouldn't be an H giver. I clicked too fast. Which of the following diagrams best represents an aqueous solution of sodium fluoride? The water molecules are not shown for clarity. Will this solution be acidic, neutral, or basic? All right, so the sodiums are with those little purple pluses, the fluorides are little minus greens, and the hydroxides are OH groups with -1, and the hydrofluoric acids are green with a little white ball. All right, first thing to know, right? Fluoride is the conjugate base of hydrofluoric acid. Hydrofluoric acid is a weak acid. So that means that fluoride ion is a significant base. So if I put fluoride ion in water, those fluoride ions will take H's off of those waters to produce hydroxides. So I'm looking at solution C, right? You've had some of those fluoride ions turn into hydrofluoric acids and make some hydroxides in the process. So this can be a basic solution. And that's what happens when you put fluoride ion in water. It'll react with the water to make hydroxide. Sodium ions are spectators. So you got a Kb value for fluoride ion. It's a significant base. Which of the following diagrams... No, the following diagram represents a reaction with PCl4+ reacting with chloride. Draw the Lewis dot structure for the reactants of the products. Identify the Lewis acid and the Lewis base in the reaction. Okay, so what's happening here is the anion is donating an electron pair to form a bond with the blue ball in the center. So the chloride, right, is going to donate an electron pair. That makes it the Lewis base. The phosphorus in the cation here is going to act as the electron pair acceptor. That makes it the Lewis acid. And we form a bond, right? Changing what was sp3 hybridization to sp3 dehybridization by hooking another chlorine onto this molecule to make phosphorus pentachloride. So again, a Lewis base is electron pair donor, and the Lewis acid is an electron pair acceptor. No change in oxidation state. If you check the oxidation state of these atoms, nothing's changed. This is not a redox reaction. This is not a Bronsted acid-base reaction. This is a Lewis acid-base reaction. The following reaction represents a hydrated cation losing a proton. How does the equilibrium constant for this reaction change as the charge of the cation increases? Okay, so when we have this highly charged cation, right? The more charge it has, the more it's going to pull electrons away from one of those OH groups and make it easier for that H to be donated to form a hydronium ion. So you get a Ka value for these hydrated cations. So for example, I simplified it. I got rid of two of the waters that are attached to the central cations, right? So with a +2 charge, you get this Lewis acid-base reaction that forms this hydrated cation. So this gives the blue color to copper-2 chloride, the pink color to cobalt-2 chloride, and so on. So these cations are acting as Lewis acids, and the waters are acting as Lewis bases to form these complex ions. So these complex ions have a Ka value. The more charge you put on that cation, the more the electrons get pulled away from one of those OH groups, weakening it, so that the electron pair gets taken by the oxygen, and it makes it easier for this H to be donated to an outside water to form hydronium ion. So these hydrated ions have Ka values. The more highly charged the cation, the bigger the Ka value. Give the conjugate base for the following Bronsted Lowry acids, right? So we have hydroiodic acid. The conjugate base of hydroiodic acid is iodate. Oh, so we're looking at the two of them, right? So ammonium ion will donate an H2 water, forming hydronium ion and ammonia. So the conjugate base of ammonium ion is ammonia. The conjugate base of hydroiodic acid is iodate. Give the conjugate acid of the following Bronsted-Lowry bases, right? So oxide is a very strong base, and you take an H off of phosphoric acid, you make something that can potentially take an H. All right, you make a potential base. So the conjugate acid of oxide is hydroxide. So this would be a ridiculously weak acid, right? So strong base, weak acid. And I have a base here because I take the H off of phosphoric acid, a conjugate base. So potentially an H can be taken off of water to form phosphoric acid. Again, this is a very weak base, and the reverse reaction would take over right away and reform dihydrogen phosphate in water. So conjugate acid of dihydrogen phosphate is phosphoric acid. Designate the Bronsted-Lowry acid and Bronsted-Lowry base on the left side of each equation, and also designate the conjugate acid and conjugate base of each on the right side. All right, so with A, we've got hypobromous acid reacting with water, and hydrogen sulfate reacting with bicarbonate to form sulfate and carbonic acid. All right, so looking at A, the acid in this situation is definitely the hypobromous acid, and water's acting as the base. The conjugate acid of water is hydronium ion, and the conjugate base of hypobromous acid is hypobromite. If I'm looking at hydrogen sulfate reacting with bicarbonate to form sulfate, hydrogen sulfate's losing its H, so it's acting like the acid. Therefore, hydrogen carbonate is acting as the base. The conjugate acid of hydrogen carbonate is carbonic acid, and the conjugate base of hydrogen sulfate is sulfate. We've got hydrogen sulfite reacting with hydronium ion to form sulfurous acid and water. In this situation, hydronium ion is acting as the acid, putting an H onto hydrogen sulfite to form the conjugate acid sulfurous acid, and the conjugate base of hydronium ion is water.